This lesson is about energy flows and systems, and the learning target is to be able to explain how energy flows are measured throughout a system. So as we look at the different types of energies that could be a part of the system, one category that we can put them into is mechanical energy, which is the total energy due to large-scale interactions and motion. So this could be either our potential energy because of interactions, or it could be kinetic energy because of motion. And so remember that we have kinetic energy, which is the energy of motion coming from this car moving really quickly. We have gravitational, and I'm going to just go gravitational energy because of the height that this person is at over the ground. And so remember that they have the potential to fall, and they could fall there. And we also have something called elastic potential energy, right? Which is because this hand is pulling back a rubber band here, and that causes it to have some elastic potential energy. If they let go, that rubber band is going to take off flying, and so it has some stored up energy in the elasticity of the rubber band. And so these three all make up the mechanical energy, and we add them together to get the total mechanical energy. So if something is moving while it's on top of a cliff, those two types of energy, kinetic and gravitational potential energy, add together to give it its mechanical energy. And so that are three different types of energy that we see quite a bit with mechanical. And we've got some other types here. Right here, we've got the energy that is held inside of a cheeseburger. And this is the chemical potential energy. This is the energy that's held between the bonds of these atoms. We have, proteins making up this burger. We have carbohydrates. We have the fats and cheese and in the burger. And those chemicals, those molecules can be used by our body for energy. And so there's energy stored in those bonds, and we call that chemical energy, chemical potential energy. We could also have the energy from sound. So sound also has energy, and so we could use that for one of our types of energy. We also have something called thermal energy. And I put this down as a picture here because this is the best Call of Duty game that has ever been invented. It's Call of Duty Modern Warfare 2 for anybody who's ever played that game before. And they had something called the thermal scope, and you would put it on, the intervention, and you would just wreck people with it. But the reason why it worked is because people's bodies give off thermal energy as heat. And so this is another type of energy that we can look at, and one we're going to look at later. We also have electrical energy, which is the energy from electricity and the electrons moving through something. We also have something called, I'm going to use radiant energy. This is also could be thought of as light energy, which is the energy given off from light sources, the radiation. And so this doesn't just have to be visible light. This could be things like ultraviolet radiation. We could have X-ray radiation. That's the radiant energy here. And we also have another type of energy called nuclear, which is the energy that is held in between the nucleus of an atom. And so we have nuclear energy, which we can harness for nuclear power sources, or we could use for nuclear bombs or anything like that. But it stores a lot of energy in those nuclear bonds. And so we have all of these different types of energy that we look at. And the cool thing about energy is that energy can be transformed or transferred within an object to different types of energy, and it can be transferred from one object to the other. And so, if a car transfers kinetic energy to something, let's say it hits something, hopefully nothing important, but if it hits something, it's going to transfer some of that kinetic energy. The other object is going to start to move, and so it's going to be transferring that energy. We can also transform chemical energy into kinetic energy as we use our chemical energy that we take in from food to help us to move. And as we're talking about that, we could have our kinetic energy that we use, in our body to move our hands, to transform that energy into elastic potential energy, to pull that rubber band back. Or we could use our kinetic energy to move us up on top of a cliff to give us more potential energy from gravity. We could use nuclear energy, which we use to harness that power of the energy between the nucleus of an atom, and we could use it to make thermal energy. Then we could take that thermal energy, convert it into steam, use that to form kinetic energy, which is going to turn a flywheel, and then that in turn could create electrical energy. And so what we're doing here is we're not making new energy, but we're transforming these energy types between one another, and we're transferring that energy from one object to another. And that's why it's important to understand the different types of energy so that we can recognize what's going on in situations in these systems and what type of energy do we have and what type of energy are we transforming that into. And so as we're looking at the different types of units, if we're looking at types of energy, we got to look at the different units of energy. And one unit that we have that you're pretty familiar with is calorie. And you think back to the chemical energy that's stored in a cheeseburger. Well, that energy is noted as calories. There's little c calorie and there's big C calorie. We're not really going to get into the calorie too much, so that's not one that I especially need you to notice. I'd like you to remember that it is a type of energy. But the one that we're really going to focus on here in science is called the Joule. The joule, capital J. And this, let me note, is how you actually spell joule. I don't know who came up with this spelling for joule, but they definitely were not listening to science class. And I'm glad that you guys are paying attention. And so you will not spell joule like that. I'm not sure who thought of that. And what a joule is actually defined as in science is the amount, it's the amount of energy needed to push with a force of 1 Newton for 1 meter. And so to move something with a force of 1 Newton for 1 meter, that's the amount of work that would be done. That's what a joule actually comes out to be. And so that's why we use this form of unit for energy in physical science. And remember, so as we're trying to track the energy flow through this system, we want to be able to have the components of a system model, the characteristics that we talked about, so that we can make sure that our system model is useful and we can understand this system a little bit better. So I'm going to draw a boundary. I'm going to draw a really wide boundary around this thing. So I have this box drawn around the different components. I have my input. Now, what we got to see here is that I can't necessarily see the input. I can see right here that this energy is coming from chemical, but that is within our system. And so we've got to see, well, where is that energy coming from? Well, that energy is coming from our food. So we have some sort of food that's being our input of energy. So we eat food, it gets turned into chemical energy. That chemical energy is going to be used to fuel the rest of this system. And so I'm going to look for our outputs here. We've got some energy coming out, leaving our system. We have light energy right here, and we have thermal energy right here. We can see the little red box and the little yellow box. So we know that we're losing light energy and thermal energy that we're giving off here. I can see my components. I have the biker, I have the generator, and I have the light. So I have those components of my system model. I can see the flow, so I can see, I don't have any arrows for this one, but what I can see is that this energy, and if this was a live simulation, you'd be able to see that this energy is moving throughout this system. And so this energy is moving around this generator here, and then we have energy flowing through here. I was going to add in some arrows, and then these guys are flowing around in here. And so we do have some flow going on in this system. And so we can see how that energy is moving throughout this system and where it's going to. We don't quite have any feedback here because our outputs here are not affecting our inputs. The amount of light or thermal energy in this system we're going to assume is not affecting our inputs. So we don't have any feedback. And for cycles, we don't really have any energy being recycled in this one. It's not like a like a carbon cycle or a water cycle or anything like that where we're using something over and over and over. So we don't really have that going on in this situation. But from this system model, if we have all these characteristics, we should be able to track the energy that's flowing throughout this system and be able to say, well, where's the energy coming from? How much is leaving? And what types of transformations are going on in here? And so if we look at the transformations, we can see that we're starting off with our chemical energy, and then that is being transformed right here through the legs into a mechanical energy. And then that mechanical energy travels through our system through here. And then at some point here, it's being transformed into electrical energy. And our electrical energy flows along. And then our electrical energy is being transformed into thermal and light energy here in the light bulb. And so by defining our system, making sure that we have our boundary, making sure we have our inputs, our outputs, our components, and our flow, especially those first 5, we can track the energy flow throughout. If we knew how much energy we were taking in from our food, if we knew how many calories or joules that we were taking in, we would hypothetically be able to know how much we were going out. Now we might have to have a very detailed model for this, more detailed than what we have, in order to be able to really track all of this, but at least give us a start. And so that is why our system models are really important, so that we can see what's happening in these systems. And so as we're talking about energy, there's one law that we have to make sure that we cover, is that the law of conservation of energy, saying that energy can be transformed from one form into another or transferred to another object like we talked about, but energy cannot be created or destroyed. Whatever energy goes into a system has to be coming out of that system. We can't make any more energy. And so we know that all energy is going to eventually either be transformed or transferred onto something else. And so that really helps us actually to be able to track the energy as it's moving through our system. But just remember that we need to have our inputs, we need to have our outputs, we have our different types of energy that can be transformed, and we measure energy in Joule, the joule. And that's really how we measure the amount of energy going in and out. So I hope that this helps you to be able to track energy moving through a system.